Welcome, Hornets. Today we're going to be taking a look at continuity. Now, when we're talking about continuous functions, we're saying that a continuous function has a value everywhere. And there are other conditions. In fact, the three conditions are as follows. Number one, the limit as x approaches a value a in a function exists. That means that it has to have a two-sided limit. Number two, the value f of a also exists. So we have to have a point at a. And then the limit as x approaches that value of a for f of a must equal f of a. So these are our three conditions. If I am looking at a graph of a whole bunch of values that are the domain, every single x value has to meet every single criteria that is here. So no matter what value I look at, let's take a look at a line, for example. When looking at the line, y equals x plus 2. You'll notice if I choose the point right there at x equals negative 1, I can clearly see that the limit as x approaches negative 1 is 1. I can also see that the value is defined at 1, and I can see that the limit where it's defined is the value that it is defined at. And this happens for every single value in the domain. No matter what we look at, no matter where we go, all three criteria will fit for any point in the function. So if I have a function like a quadratic or a cubic or a quartic or linear absolute value, every single point is defined in the domain. And the limit exists for every single point. And the final criteria is that for every single limit, the limit and the value are equal. All right? So that's what we have to watch out for. So let's take a look at our situations and see what can happen. First of all, a limit can exist in many ways, yet still fail. For example, here we have a graph that has a hole in it. The limit, as I approach this value, will say that this is approaching a, and this value is p. I can clearly see that according to my finger test, or Heathcliff and Catherine coming in to kiss each other, that they will indeed kiss each other. They will meet at p. So the limit as x approaches a for this function is p, and it satisfies the first criteria. But you'll notice f of a does not exist. That's a problem. Right there, it's failing the second criteria. And because it's failing the second criteria, this function is considered discontinuous or not continuous. Now, we can even do something a little bit more extreme. Let's take the same graph ooh, ah. Now we're still approaching P as we approach A, but now I'm going to define it up here at Q. Notice that the limit exists. The limit as x approaches A for this function is P, and f of A is Q, which means that the point exists. But now it's failed the third criteria. The limit as x approaches A for f of x does not equal f of A. And that's a problem. And therefore, this function is also discontinuous. Okay, notice, holes in the graph, the limit is existing in these situations, but the value is either not defined or the value is specifically defined in another place. This is referred to as a removable discontinuity. And it is a very, very special discontinuity. We call it a non-essential. So this is a removable discontinuity. A removable discontinuity is defined as having a limit that exists, but the value is either misplaced, they are not equal to the limit, the point that's been defined, or the point doesn't exist at all. Okay? The way you know you could possibly be dealing with a removable discontinuity is the limit exists, but it's still discontinuous. All right? This is very important. Now, the reason why we call this a removable discontinuity is because as mathematicians in calculus, we have the choice to redefine values by making a piecewise function. After all I need to do here is say that I have this function f of x, and it's something else for all values of x not equal to a. And then it will equal p at x equals a. And by simply altering into a piecewise function, I fill in the hole. Once again, a removable discontinuity means that the limit is going to exist, but the value is either misdefined or not defined at all. To clean this up, as mathematicians in calculus, we make a piecewise function and we fill in the point correctly. This then fills in the point and allows it to be continuous. So we can change removable discontinuities and make a function continuous, through a piecewise function. The second type of discontinuity that we have is even more obvious. These both are going to be called essential discontinuities. And we say essential because they cannot change. You'll notice with the removable discontinuity, we could change it with a piecewise function, but not with essential. Essential cannot change. They are locked in stone. For example, let's take a quick function that has two different values of limits. This one we will have as p, and we're going to go ahead and we're going to start down here. Let's call this q, and q goes on. Notice in this graph, the limit from the left, as x approaches a, for our function from the left, we get p. And the limit as x approaches a from the right, we get q. And because we have two distinctly different values, the limit does not exist. So when the limit doesn't exist, you will have an essential discontinuity. This is referred to as a jump discontinuity. It happens because I have two different one-sided limit values, and the two-sided limit doesn't exist. That's one of our criteria for an essential discontinuity. The limit doesn't exist from two sides. Now, if we keep that in mind, the obvious other discontinuity is at an asymptote. I'm going to go ahead and I'm going to put my discontinuity here at a again, and identify it as x cannot equal a. Now let's just go ahead and draw a reciprocal function. And you'll notice that the limit as x approaches a from the left, the limit as x approaches a from the left for this function is positive infinity. Yet the limit as x approaches a from the right for this function is a negative As a result, we have to be careful and recognize that they're opposites. The limit does not exist here any more than the limit exists here. So if you see that the limit does not exist, look to see if you have two different values or whether it has an asymptote. Now we can mix and match these, and as we mix and match them, we can see other possibilities. Thank you very much. We will be continuing in the next video.